Okay, so here's the plan. So I'm in text next Thursday. We're gonna get through as much as I can today of the end of chapter 4 and chapter 5. Whatever I don't finish covering today, I will cover on Tuesday, and then we'll use the rest of the time to review. I will have the review test up. I didn't have it printed today because I wasn't exactly sure what I was going to get through. I will have the review test up today online in the post, so probably by the end of the day. And then so you guys can print it out and stuff like that, work on it, and then we'll do it. We'll go over some of the stuff next Tuesday, depending on how much time I have left. All right. All right. So the piece we didn't get to at the end of chapter 4 is kind of important for chapter 5. So we got to go through. It's basically about combinations and permutations. So let's look at a couple quick examples. First one is license plates. So when you're looking at combinations of things, you basically want to look at boxes. Like how many, when we're counting, it's like how many different possible combinations do we have? So for license plates, we have letters and numbers. So, and they can repeat themselves. So if we have 3 letters followed by 3 numbers, which is actually what Connecticut's license plates used to be. So we have 6 boxes. How many different things can I put in the first box? Right. How many things can I put in the second box? 26. Third box? Fourth box? Almost. 10. And then 10, and then 10. So when we're counting, all we're going to do is take these and multiply all the numbers together. So we've got 26 times 26 times 26 times. So in the A situation, I can have 17,576,000 license plates. So what changes from A to B? They can't repeat. All right, so we're going to do the same thing. We're going to have our boxes. All right, so how many boxes in the first box? How many is in the second box? 25. Because whatever letter's in the first box, I can't use again. How many is in the third box? 24. Because again, it's 1 less. Because I have now 2 letters I've already taken out of it. So there's only 24 possible letters in it. I don't know which letters those are. It doesn't necessarily have to be the same letter, but there's just 24 different things I can put in there because I've already used 2. What about the fourth box? That's 10, and then 9, 8. And then 8. Because again, it goes down based on that. So if we don't replace, we multiply those, and we get 11,232,000. So just 3 letters and 3 digits, I can have 11 million different plates if they don't repeat, or 17 million if they repeat. It's a lot of license plates. And the thing, we ran out of license plate numbers and we had to change the place around it. So now it's 2 letters followed by 5 digits is the majority of the plates. All right. So a couple little terms that you're going to see. A factorial, you might have seen the symbol before. It's a little exclamation point. That actually is a mathematical symbol. It's not, yay, 3. It's 3 factorial. That means 3 times 2 times 1. It basically means that number times every other number all the way down to the end. Okay. So the 5 factorial would be 5 times 3, or 5 times 4 times 3 times 2 times 1. Okay, that's what factorials are. You're not going to have to use it as much as the book has you use it as, but I wanted to at least let you see what it was, because I'm going to have you guys use Desmos or Scientific Calculator to be able to do the combinations and permutations instead of having you do the formula out, okay, which would use the factorials. But I do want you to actually know what that symbol means, because it does come up quite often in things in math. So, yeah.
After the parentheses for the 1, isn't that just times 2?
Yeah, it's basically, it's because it's every single number all the way down, and it always ends in 2 times 1.
Okay.
So it's whatever k is. So if k was 10, it'd be 10. 10 minus 1 is 9. Times 8 times 7 times 6, and then times 2 times 1. So it always ends in the same thing at the end, because every number goes all the way down to 1. You don't go to 0, because if you multiply it by 0, it'd be 0. So it ends at 1. All right. So as you can see, the formula has the factorial symbol. We're not going to use the factorial symbol. We're going to use Desmos to do it. But the difference between permutations and combinations, which is the next thing we're going to look at. Permutations, order matters. Okay, so permutation, order matters. Combinations, order does not matter. What that means is that 3, 2, 1 and permutations is different than 1, 2, 3. Okay, so 3, 2, 1 and 1, 2, 3 are 2 different things, and it would count as different in a permutation. And a combination, 3, 2, 1 and 1, 2, 3 are the exact same thing. So we don't need to count it twice. All right, so when we're looking at permutations, you'll see it's listed as 2 different ways. Like this one is the M and then the P and the R. Where you're going to typically see it on the computer, it's an N and an R. I don't know why they used M and not N. Typically you see N being used. This is what you're going to see when you typically look at a graphing calculator, stuff like that. You might also see NPR. You might see that as well. So either one of those mean the exact same thing. The N is the number that you have, and the R is the number that you're choosing. So in this problem right here, I have 12 entries, and I'm picking 2 horses. So it's 12 P2. So in Desmos or your scientific calculator, you're going to see, if you click on function, you'll see NPR and NCR. So I put NPR, and then it's 12, choose 2. Yep. Yep, you just put a comma between it. That's okay. Yeah, it's a comma. So you're just choosing, it's 12, and you're choosing 2. And there's 132 different combinations or permutations of that. Because if you're picking an exacta, if horse Secretariat wins and Amazon comes in second, that's different than if Amazon wins and Secretariat comes in second. For some strange reason, I couldn't come up with another name of a horse. Like that would be two different combinations. Okay. So that's where it says order matters. That's why we use a permutation for this situation. Okay. All right. Combinations. Order doesn't matter. But it's set up the exact same way. You're going to see NCR or C and comma R. You'll see either one of those two on the things. Is anybody in here old enough to remember Columbia House? Nope. So back in the 80s and 90s, before we had computers and Napster and downloads and streaming services and everything else like that, you used to have to get CDs and tapes and things like that. So Columbia House was a company that would give you 12 tapes or 12 CDs for a penny to start with. But you subscribed to their service, and then you had to buy another 12 at whatever their cost was. They ended up going out of business because way too many people would just buy the first ones and then just ignore all the other bills after that point and never pay for the rest of them. But does it matter if I choose Lady Gaga's new CD and then 3 Days Grace's new CD? Does that matter if I choose 3 Days Grace and Lady Gaga? No. So order doesn't matter in this situation. They're the exact same thing. So that's the difference between that and the horses. The horses, the exact that matter. In this case, it doesn't make a difference. I still get the two CDs. All right. So you buy one CD at regular club price, you get 4 free. And the choices are out of a collection of 69. So how many different ways can I select 4 CDs? So in this case, because order does not matter, I'm going to use combinations for it. So I'm going to have C. I have 69, and I'm choosing 4. Right, does that make sense on how we set it up? And since we're using the calculator, I'm not going to have to go through and use the whole formula that's there with the factorials and everything else like that. So if we go back to Desmos, I use NCR. I'm doing 69, and I'm choosing 2. So NCR, when I did it, I get 2,346 different combinations, which would be the answer that we're looking at for this one. Oh, yeah, 2,346. Oh, is it 4 CDs? Oh, you're right. It is 4 CDs. I was going back to my other one. You're right. 4. So we change this to 4.
How did they get 69 times 68 times 67 times 66?
Don't worry about that. I'm serious.
Okay.
Because so they're using the factorials. They're doing it out by hand. I'm not having you ever do this out by hand.
That's how they got 864,501.
Right, which is what I just got when I changed it to 4 instead of 2. So you can start to see how these numbers can get really big really quickly. So there's 864,501 different combinations of CDs that I can pick. If ordered mattered, notice how it's a lot more. It's over 20 million different combinations. Okay, so when order doesn't matter, you're going to get a lot less options. Okay, because again, you don't have, you eliminate all the duplicates basically in that situation. Okay.
So what does R mean in the combinations rule? The number of possible combinations or the objects?
Huh?
What does R mean in the combinations rule?
R is how many you're choosing.
How many you choose?
So N is, or the way in the book did with M is how many you have, or how many options you're picking from. And then R is how many of your choices you're making from that. R will always be either the same or smaller than N. It can't be bigger because I can't choose more than I have. It can be exactly the same. And actually, if we look at that, like if I change this to 69, if I have 69, I'm choosing 69. What would you think the answer would be? If order doesn't matter.
Wait, repeat it.
If I have 69 of them and I'm picking all 69 CDs and order doesn't matter, how many different ways could I do that? One way. Okay, that makes sense, right? Because order doesn't matter. If order mattered, it'd be almost a Google ways to do it. Okay? Because then I'm listing all 69, and the 69 in order is different than if I switched one. Okay? So that's the major difference when you're looking at order matters and order doesn't matter. Okay? All right.
Could you repeat what M meant? Because I didn't get that.
How many you have?
How many you have?
How many you're choosing from?
I thought that was R.
No, and R is how many you are choosing. So like if I have a deck of playing cards that's 52 cards and I'm choosing 3 cards, it's 52 is N or M, 3 is R. Okay?
So M is how many you're,
How many options you have,
how many options you have.
and R is how many you're choosing from them.
Okay.
And R is always smaller than.
Yeah, or it can be the same, but it's always got to be the same or smaller. It can never be bigger because, again, you can't choose more than you have. And that's how you read it. It's like the first one. I have 12 horses. I'm choosing 2. So I'm choosing 2 horses from the 12. The chooses is your R. The how many you have is the M or the N. Everything you see online or anything on a calculator is always going to be N. You're never going to see M. I don't know why the book used M. All right. Just because you are going to see them written like this symbol right there, that right there is another way to write NCR. Okay. If you see that, that is NCR. So that first one right there, A, is 6, choose 1. B is 5, choose 3. Okay, does that make sense? Okay. And then we would just go to the calculator. And type in 5, choose 3. And you get 10 for that one. And the first one was what? 6, choose 1.
Yes.
6, choose 1. 6 times.
When it shows up like this, how do you know to use NPR versus NCR?
These will always be NCR. So this symbol right there is always order doesn't matter.
For the first one, couldn't you have written 1, C, and then 6?
No.
Doesn't matter.
So no, because remember, the first number that you put in is how many you have. So if I put in 1 and I'm choosing 6, I can't choose 6 things if I only have 1 thing to choose. Okay? The biggest number always has to be first. Because if you read this, the easiest way to read this is 6, choose 1. 5 choose 3. So I have 5, I'm choosing 3.
Okay.
I can't have 1 choosing 6. And if you try to do it,
I want to see what happens. Oh, that's 0.
right, because there's no way to do it. Okay. Because I can't choose 6 if I only have 1 thing. The other thing is like I can't. It's like I can choose 0. That is a possibility. There's just only one way to do it. Okay, I pick none. That's it. So you can choose none. That is a possibility. All right. Any questions with combinations and permutations? Yes.
So if it's 6-1, will it always be just like 6, or if it's like 15-1, will it be always 15?
Yeah, if you're choosing it because you're choosing just one of it, yeah, you can pick each one once. So yeah, it always ends up being the same.
And then if it's like 5-5, it's always going to be 5.
No, it'll always be 1.
1. Okay.
In choosing, it'll always be 1. All right, let me give you one problem with this. No, I'm not a Dodgers fan. I'm a Yankees fan, but my favorite player is Don Mattingly, so this problem still is nice. All right, so from the 2013 Los Angeles Dodgers, they had there were 5 active players that could play the outfield. For anybody who doesn't know baseball, how many outfield positions are there? There are 3, left, right, and center. So, assuming that these 5 players could play any of the outfield positions, how many different assignments could Mattingly have made for the 3 outfield positions? Step 1. And does order matter or does order not matter? It does not matter. Okay. Because they're still just going to the outfield. Actually, wait. I take that back. Is right, center, and left different than center, right, left for the player? Yeah. Because I'm going to stick them in the outfield, right? But I still have to tell them where to go, correct? So if I have 3 players, that first player I have to tell is going to right, center, or left. Okay, true? Okay. So picking them for 3 outfield positions and not telling them where to go, order doesn't matter because, yes, I'm choosing these 3 players to go. However, because the 3 outfield positions are different, and I'm not just going to have them all go stand in the middle of center field, which is now actually in baseball illegal because you can't shift anymore. I have to tell them where to go. So since I have to tell them where to go, order does actually matter because there's 3 separate positions. So in that case, am I using permutations or combinations? Permutations. So this is P. So we're using NPR. So how many players am I choosing from? 5. And how many players am I choosing? 3. So it's 3, 5, E3. And we go here. And there's 60 different ways that I can do it. So there's 60 different outfield setups that I can have with those 5 players. So you can start to see how that's the only question that in essence, when you're doing permutations and combinations, you have to ask. Does order matter or does order not matter? Typically, when you're looking at doing positions, order matters. Because like even if you're doing president, vice president, treasurer, secretary, things like that, order matters because they have different roles. Okay. Places on a podium, order matters. Right? Because first is different than third. Okay. So those are the ways you want to start thinking about things. All right. Moving on to chapter 5. Let's see how far we can get in 45 minutes. All right. A random variable. So there's some first things we have to lock some terms. A random variable is a quantitative variable whose value depends on chance. What does quantitative mean?
Number based.
It's number based. Okay. So it has to be numeric because otherwise we can't do calculations with it. A discrete random variable. What's the word discrete mean?
Unusual.
Nope. There's continuous and then there's discrete.
Something that ends.
So continuous is everything. And there was, huh?
Whole numbers.
Yeah, in essence. It's, remember when we talked about like the line graph where we had the dots in the line? The line is continuous. Every value between those 2 points makes sense. Okay, so that could be a random variable. When we're talking about discrete random variables, there's discrete values. So the examples are when you're rolling a die with some of the dice. Those are discrete variables. I'm going to have 2, 3, 4, 5, 6. Not 2.5, not 2 3/4, not 2 1/3. Those won't work. So those are discrete. The number of puppies in a litter, discrete. I can't have a half a puppy. Remember that was the old concept of thinking about, can I have a half of something? Return on an investment. Now, that one's a little gray because I can go down to the nearest cent. You're typically not going to go further than that. So some people think of that as discrete because I can't have a half a cent. I would lean more towards that would be continuous. The lifetime on a flashlight battery, that one's discrete because there's an endpoint to it. Okay, it has a specific end on how long it's going to live. We're not going to do that slide. Actually, no, all right, this one, we've actually talked about this before. It's just, we're looking, remember when we did the distributions and the histograms? We divided. The only difference between that and this is those divisions are now a probability of something occurring, okay, instead of just a in that specific sample. So because they are discrete random variables, we can have specifically like this is going to occur this many times, this is going to occur this many times. That's a probability distribution. We also could put that in terms of a histogram and draw it out so you can have it visually. They're very similar to what we looked at before when we were doing relative frequency. They're basically the same thing. Just like the first test, you're not going to have definitions like on the test. So you're not going to have to like say, okay, what's this definition of a word? I'm never going to ask that. All right. So we have mean. So just as with everything else, we have the ability to actually, I want to show you one thing before that case. So this is a probability distribution. Okay. So this happens to be the number of minutes somebody waits at a bank, or the number of busy tellers. I think this was the number of busy tellers. So that's the probability of each of those occurring. All right. So if you think about before, this would have just been my relative frequency. Because how many times did 4 show up? How many times did 5 show up? How many times did 6 show up? Okay. So relative frequency and a probability distribution are very similar in that respect. The question is how do I find the mean of this? Okay. And it's actually very similar to what we did when we did weighted averages. So if you have a teacher who says quizzes are worth 30%, homework's worth 20%, and tests are worth 50%, for example, I can't just add everything up and divide by how many I have. I have to weight it. So I have to add up all the homework assignments, multiply that by 20%. Add up all the quizzes, multiply that by 30. Add up all the tests, multiply by 50 to get my average or to get my mean. That's what we have to do here. So when we're looking at the mean of the random variables, we're going to multiply these and then add them up and then divide. So we're going to take how many of those things occur. Okay. So let's do that. So step 1, multiply the x by the probability of it occurring. So do that now. All right, so you're going to take each one and multiply it by the probability of it happening. And now to find the mean, we add all them up. And we get 4.118. Yeah, this is the number of busy tellers. So if you were to look at this data over here, where would you think the middle would be? Looking at the probability.
1.55. Or
3. If you're gonna do that,
Three.
it'd be 3. So if you're just looking at these numbers, yeah, 3 would be kind of in the middle, right? However, remember, these are the weights. So these numbers down here are very small in terms of how much weight they have. These numbers up here are a lot bigger. So what's going to happen with this? This is going to pull it this way, right? So the median probably would be 3, somewhere around there, right?
Yeah.
But the mean, this is going to pull it. So the mean might end up being somewhere. It's like if we just look maybe around 5, but there's a little bit more here than here, so that's where it pulls it down to the 4. So the 4.118 makes sense. Okay. One of the things that I want you guys to start looking at is especially when you do a bunch of calculations, does the answer you get at the end make sense? Okay. Because if you're doing calculations and you get a number that's way out there, you should recognize that it's way out there and fix something. Okay. So like if you had gotten a number like 10, there's no way that makes sense. Because there's not even a 10 on the screen. So you screwed up. Odds are you missed a decimal point somewhere. Okay. And so I can go back and look for that mistake. Because when you're using a calculator, it's the whole garbage in, garbage out. Like if you miss putting a decimal point in your calculator, you're going to get an answer that doesn't make sense. You've got to recognize that it doesn't make sense and fix it. All right. So that's part of the process that we're doing with these things. Okay. So for mean, you're going to treat this like a weighted mean. You're going to multiply how many you have by the probability and then add them up at the end. We don't have to divide at the end because we've already divided with the probability. So they already did that step for us when they got the weight, the probability or the relative frequency. We don't have to divide again. All right, questions with that? We good? Okay. Okay, talked about that already. All right. All right. Unlike, unfortunately, when we did standard deviation, we were able to type all the numbers in and get the answer. Unfortunately, in this case, you really can't do that because of the way that the numbers are, because they're weighted. So if you're going to try to type them in, you'd have to type in every single number, and sometimes that could be thousands of numbers. So there's an easier way to do it. There's a formula for it. And it's not overly difficult to do. The only difference is we have to square the numbers and then multiply it. So if we're looking at same setup that we had before, we know our mean. So we have our mean is 4.118. We've got that. We know that number, which is good. The formula for it is the square root of the sum of the x squares minus the mean squared. So what we have to do is we're going to square that number and multiply it by that. So it's 0 squared times 0.029. It's 1 squared times 0.049. It's 2 squared. So the only difference between when we found the mean and we found this one, you have to square it. So if you, and then you're going to do the same thing. You square them all up and add them up. You get 19.438. Yes, totally cheated. I just stole the answer from the book. All right. So the only difference between mean and standard deviation is we're squaring instead of just taking the number as is. And then to find my standard deviation, we're going to take the 19.438 minus 4.118 squared and take the square root of that. So you take the 19.438 minus the 4.118 squared, and we get 1.575. And that's my standard deviation. Those are my favorite casino games, roulette. What did I say about betting in black and red? It's not 50-50, right? Or most people would think it's 50-50, but it's not because of the green. So if you were to just bet, say you left it on black the entire time, or actually in this case they said red. You bet $1 in red every single time. The probability that it's going to hit, that red's going to hit, is 18 out of 38, which is 0.475. The probability that it's going to miss or hit something else is 20 out of 38, or 5.26 or 0.526. Okay, does that make sense? Do you understand how they got those two numbers? You can tell me no, it's fine. All right, if I hit, I win. So I win $1. If I miss, I lose $1, right? Okay. What on every roll or every spin, How much money do I lose?
$1.
No, I could win $1 or lose $1. So, in essence, what it's asking for is the mean. What's the average loss on every roll or every spin of the wheel? Okay. So, because I can win or I can lose. But if I did it long enough, I'm still going to be able to get an average. So, how do I find the mean of this? So do what I did before and find me the mean. I specifically chose one that only had a couple things to multiply and picked the numbers that were quite easy to multiply. That's the mean. So if I was to play 100 times, how much money would, on average, I have after playing 100 times? Well, if I'm playing 100 times, I have $100, right? Okay, so how much would I have left in front of me after 100 times? Approximately $95. Okay. Every spin, I lose basically 5 cents. So if I played 100 times, I'd expect to have lost about $5. Okay. On average. You could walk in there and walk out with $1,000, winning every time. Or actually, it wouldn't be $1,000; it'd be $200 because you double your money. But on average, that's what you'd expect to happen. That's the house's take. That's how casino games are designed. Okay, they have to play on the averages. And when there's thousands of people coming in and playing, and there's thousands of spins of the wheel and 1,000 rolls of the dice and everything else, that's how they make their money. That's how they keep the casinos running. Because those 5 cents add up quite a bit. The slot machines are way worse odds. So the slot machines are probably so roulette's about 95% your expected winnings. The slot machines are closer to 70 or 80%. So
if you gamble, you want to play the black.
you'd want to play craps. Actually, craps is even better. But you definitely want to play the table games over the slot machines. Okay, but if you walk into a casino, where do you see everywhere? Slots. and they're colorful and they have funny names and funny games, and there was fish and lights and everything else. They're drawn to that. Most people that go to a casino are scared of the table games because you have to know the rules. Slot machines are easy. Put $5 in or $20 in and press a button. It's either you win or you lose. It's like a scratch ticket. It's like, yay, you win, or nope, you lost. It's like, doesn't make much difference. The table games, you have to know the rules, you have to know how to bet it, things like that. It's a little more intimidating, so most people don't play it. But yes, you're going to make a lot more money if you play the table games. Well, either you're going to lose a lot less money, I should say, if you play the table games than if you play the slot machines. Right? But that's how they figure it out. That's why mean and standard deviation, those things come into play.
How did you get negative 0.052?
Added the two numbers together. Remember, mean is you do the multiplication and you add them all together. So if you added 0.474 plus negative 0.526, you should get negative 0.052. If I did the calculation quick in my head right.
Oh, okay, yeah, that's right.
Okay. Like as long as I did the calculation quickly in my head. So that's that piece. That's there. All right. I saved that for Tuesday. Let's do one more of these. Unfortunately, I'm not going to have time to finish the next section, so I'm not going to start it. So we'll do one more of these problems, then we'll call it for the day. Insurance. Insurance is like gambling. There's two really, really lucrative jobs if you ever want to be a mathematician. One is investment banking. The second one is actuarial science. Actuarial science is basically determining risk for insurance companies and individuals. So when you go to an insurance company, they have to determine how much of a risk you are. And based on that, that's how much they charge you. There's mathematicians in the backgrounds figuring that part out for them. So that the person on the phone with you literally just types your information into a computer and it tells them how much to charge you. So an insurance company wants to design a homeowner's policy for mid-priced homes. So this is the data and the amount of annual claims that they get in thousands of dollars. So it's $0, $10,000, $50,000, $100,000, $200,000 with the probability. They want to make money. All right. So if they want to be able to make at least $50 per policy, how much should they charge for the policy? So the first thing we have to figure out is what? We have to figure out the average amount of money they pay out, right? Because if we can figure out the average amount of money they pay out, then we just add $50 to that. That's what they're going to charge. So find me my mean. Find me the average amount that they pay out per claim. All right, so if you did it out, you should have gotten 0, 0.45, 0.2, 0.09, 0.02 for each of the different values. Then we add all those up, and we get 0.76. Yes.
Just a quick question. Why didn't we square the numbers that came before the parentheses?
We're not
like
looking
we-
for standard deviation.
Oh,
We're looking for mean.
yeah, that's what I did. So I got 117.5 out of doing that.
Yeah. We're looking for mean, not standard deviation.
Oh.
And even if you're doing standard deviation, you always have to find mean first because I have to subtract off that part. So you have to find your mean first.
Wait, what part are you specifically subtracting out?
So for standard deviation, you have to find that part, which is what you did,
Yes.
minus the square of the mean.
Minus the square root of the mean.
The square of the mean, that's square, and then you take the square root of the whole thing. So I purposely didn't do standard deviation because I knew it was a bunch of extra steps. All right. And standard deviation, remember, just tells me how much the spread is. So the reason we would use standard deviation, so we have the mean, and if we then found standard deviation, we could find out, okay, this is 1 year. From year to year, it might vary by about this much. So, and that's what the standard deviation would give me. It's like, okay, it's like, yes, this is what I've got now, but it could vary from here to here. It's like, if I want to still make more than $50, I might go on the upper end of one standard deviation. I might add that to it just to have that little bit of an extra cushion in case something bad happens. And in all honesty, where your insurance companies are, like, we think they're robbing us blind. They're working on very small margins. They really aren't making a ton of money. Because when disasters hit, they spend out a ton of money that they've collected over time. So it's like, it's one of those things like you hope you never need it, but you have it in case you do. All right, so these were all in what? Okay, but what was, yes, there's an screen, but what was the original problem stated all this was in what? What was the claims in? Thousands of dollars. So it's 0.76 thousands of dollars. How much is that in actual dollars? We multiply that by 1,000, we get what? $760. Okay, so the average claim is $760. Okay, does that make sense? And if you look at the numbers, it kind of makes sense. Like 95% of the people don't make a claim. The other 5% make a claim. So if I have a $760 is my claim amount that I'd be paying out, how much should I be charging if I want to make at least $50 on each policy? I'd sell the policies for $810. You're never going to find an insurance policy for your house for $810. Like my house insurance, I think, is like $2,700. No, a year. This was, I think this was annual. The problem was written. Yeah, the annual claim. So this was annually. And what happens when you make your first claim? They raise your rates. Because you become more risky. And depending on where you live, depends on the risk factor. You have a house at the beach, you're probably going to get charged more. You have a house in the city, you're probably going to get charged more. So a lot of those little things come into play. Right? But this is how the stuff that we're talking about is really actually used and how it actually impacts you on a regular basis. Okay. All right, so we're through. The only thing I haven't done is the binomial distributions, which we'll do on Tuesday. So I will do that, and I'll review. So your test is still going to be on Chapter 4 and Chapter 5. There's a few little things that I skipped that I'm probably not going to put on there, but it'll be about the same. It'll be 7 questions. I think that worked out pretty well for the most of you to finish in time. So, and I'll break it down so if there's multiple part questions, same kind of concept that we did last time. Yeah.
Are we going to be allowed to use a note card?
Yep.
like we
You're
did?
always allowed an index card. One index card. So, and looking at the sample test, you'll figure out what you need to put on the index card for your actual test. Okay?
You're posting the test today?
I should have, that's literally what I'm gonna go do right now. I'm gonna do my lesson for my class tonight, and then I'm gonna write up the test. So yeah, the test should be posted up there today. Okay? No problem. Any other questions? All right, I will see you on Tuesday. Yes.
I have this calculator, and for like the NPR, for some reason I can't get it to work. So it's, I see it here, but I don't.
Okay, so you have to put in the number first.
Okay.
So that's the number in the
And then
middle.
for shift, I did the.
Yep,
I did
so
that.
shift that. So you'd have to put in, so let's say, what was it, 69, choose 4.
Okay.
Okay.
Cool. Thank you.
Well,
Do you have any videos live during class, or you just to ask them?
they can be, if you send me an email, so